There are three other indeterminate forms which we have not really spoken of as of yet. I want to include now that we have the power of L'Hopital's rule to work with. So we know we already have the indeterminate quotient, which comes in many guises, right? 0 over 0 and some type of infinity over another type of infinity. And although L'Hopital's rule applies specifically to indeterminate quotients, that's not the only indeterminate form that's out there. So the other types would be an indeterminate difference, and that would be if you had two functions subtracted one from the other, and if that was approaching some type of infinity, and then you're subtracting, that's that subtract here, another type of infinity. So if both f and g are heading towards the same type of infinity, then subtracting them off does not reveal what the answer should be immediately. In other words, a person might think the answer should just be 0, but such is not the case necessarily. It could be 0. It does not have to be, again, because these are not numbers. This is just growing without bound, and this is growing without bound. So you take two things growing without bound, you subtract them. It's not clear that when you subtract this one off, it's going to prevent this one from still attaining higher and higher values for this difference. It will depend on who's growing faster, in a sense. If the second one is growing faster than the first one, then you might end up with a negative quantity for your answer, or it might just be negative infinity. If the first one's growing faster, then you might end up with infinity, because this is not really subtracting off enough to compete with this one's rate of growth, and you might end up with infinity or something in between, some finite value. They might be very comparable to each other. You might end up with a 0. So it's an indeterminate form for that reason. You have an indeterminate product. So you have two functions multiplied together. One of them is heading towards 0, and the other one is heading towards some type of infinity. Again, we don't know who's going to win here. Although the product with 0 is attempting to knock this down to 0, but this is never really 0. It's just very close to 0. So if this magnitude here is large enough, even if you're very close to 0, this magnitude, if it's growing faster, then this one is shrinking towards 0. This one could outweigh it and multiply a gargantuan growing set of numbers onto something close to 0. It could still be very gargantuan. So it's not obvious from this product which one's going to be, or again, it could be something in between, as we've seen before. So then there's indeterminate powers, of which there are three types. There is the 0 to 0, let me use the function symbols again, sorry. F of x raised to the g of x power, you might say. So if that heads towards one of three cases, could be 0 to the 0th, could be 1 to the infinity, or infinity to the 0th. Okay? Each of these is indeterminate for a different subtle reason. So if you think about the first one, if the base is going towards 0, then 0 to any power is 0, except 0, which is 1, right? So as the base gets closer and closer to 0, the overall structure here, right, this exponential structure wants to head towards 0. But as the exponent heads towards 0, that's attempting to cause this to become something close to 1. So again, how these work in tandem, it's not clear. We don't know what it's going to become, because again, these two values, these two functions, right, f and g, are never actually 0 as you run the limit. It's getting very close to. So to here, this structure wants to become 1 because of the base, but because the exponent, it wants to grow without bound, right? You have a number very close to 1, 1.000001 or something, but you raise it to extremely gargantuan powers, that can easily tear this value away from being close to 1 and make it grow without bound. So it's hard to tell initially, just based on looking at it, that it's 1 to infinity, that it's going to be 1 or it's going to be infinite or something in between. And then the last one, the base is growing without bound, and the exponent is heading towards 0. So as the base grows without bound, well, this whole expression wants to become infinitely large. But as the exponent heads towards 0, again, that's trying to knock the, just like this one here in a sense, it's trying to knock the whole thing down back to 1. Right? So how these work in tandem is not so clear upon first inspection, and it'll take a lot more analysis to figure out what the limit might actually be heading towards, or whether it doesn't exist at all.